I think one of the challenges, especially people kind of jumping into this space right now, is there's just so many models out there. There's closed, there's open source, big, little. When starting some kind of new project, like how do you even pick? Like, where do you start?
I generally like to recommend that people start with the largest, most capable model when they're in the experimentation phase. Unless there's some constraint that means you can't do that, like if you're building exclusively for edge inference on an iPhone or something. If you're starting with the most capable model, that eliminates one constraint during this experimentation and prototyping process, which is, oh, is my model not good enough?
When does it make sense for somebody to fine tune a model?
So I saw there's this great tweet that goes around a lot. No GPUs before PMF, which is the idea that you shouldn't be making these very capital intensive investments in training and fine tuning ahead of figuring out what you actually want to build.
So in terms of inference, like what is the expensive part of inference? Like why is that particularly like a slow operation? Hey everyone, thanks for joining. Today we have Philip Kiely from Baseten on the show. We go deep on inference optimization. We cover choosing a model, discuss the hype around compound AI, choosing an inference engine, optimization techniques like quantization and speculative decoding, all the way down to your GPU choice. There's a lot of meat on the bone in this one, so I think you'll enjoy it. As always, if you have questions or suggestions, feel free to reach out to me or Alex. And with that said, let's get you over to my conversation with Philip. Philip, welcome to Software Huddle.
Thanks, Sean. I'm super glad to be here today.
Yeah, thanks for being here and glad you reached out. So to start, can you give a little bit of background about yourself and the work that you do at Baseten? Like, how did you end up working at an AI inference company, and what was your background in AI prior to that?
I joined Baseten 2 years, 9 months ago. So I've been there in startup years basically forever.
Yeah. It's like that's at least a decade in real world.
Yeah, exactly. So I joined as a technical writer, and have since moved into more developer relations type stuff. But it's a 50-person Series B startup, so titles are titles, roles are roles. It's really just about doing what you can do to drive what needs to happen every single day. Anyway, Baseten itself is a model inference startup. So we're an AI infrastructure company that focuses on inference. We run open source, fine-tune, and custom models with really high performance on GPUs that can be distributed across multiple clouds, your cloud, our cloud, some combination of the two. And, when I joined, it was more of a data science facing tool. Back then, this was before GPT 3.5 was out. This was before ChatGPT, before Whisper, before DALL-E and Stable Diffusion. So it was a somewhat different market and audience. And I joined with very little background in AI or ML. I got like a B- in statistics in college, but I was able to learn on the job. And the cool part about my job is I basically just get to talk to all of our engineers, find out the cool stuff that they're working on, and then write it down and have it make sense. And in order for that to happen, it needs to make sense to me first. So basically, my job is to learn really interesting things and then share them with the world.
Yeah, I think I always found like a way to, for at least for myself, like to really internalize something and to learn it is to like force yourself to try to teach it to somebody, because you have to understand it enough that you can like teach another person. And writing is a one form of teaching, and then of course like actually teaching and or public speaking or whatever it is. It becomes like a forcing function for you to learn different things. And I even feel like I use the podcast medium for that, as it becomes a forcing function for me to learn about different topics where I might not necessarily know or have deep expertise in.
Absolutely. I can't go up on stage in a conference or meetup or something and just wing it. So there's a lot of learning that goes into every single one of those things. That's where that forcing function comes in, like you said.
Yeah, and it has to feel authentic too. And I think that's where, based on my own experience, sometimes in very technical products, selling to technical people, salespeople can kind of struggle where even if they have a script and they have, they've been trained and they have a first call deck, it's like they're speaking a foreign language in some ways, because it's just never going to be sort of at the comfort level as somebody who's like actually worked in that space as an engineer and can kind of deliver the same material.
Absolutely. That said, I have worked very closely with our salespeople to help train them and do sales enablement in some of this technical material. And, I've been really impressed by how they've grasped the complexities of stuff like, the different GPUs and how they have various capabilities, the different model inference frameworks, the model performance optimizations, the different modalities. There's a ton to learn. So I've learned it, and it's been cool helping them learn it as well.
Yeah, I didn't mean to dox all salespeople. I was yeah, absolutely. I think there's some great salespeople out there that are going to be able to grok this stuff. But going back to Baseten, like, why focus on inference alone? Like, why be essentially an AI inference infrastructure company?
That's a great question, and it's something that we kind of found our way into, because originally when I joined, the platform was much broader, and we've experimented with other things. We did a whole fine-tuning platform maybe a year and a half, almost 2 years ago at this point, as an experiment. And what we found was two things. Number one, we're a pretty small company. At this point, we're 50 people. We need to focus on being the absolute best at one thing and own the right to enter other markets in this AI space. And the second thing is that inference is really where a lot of the value is. You need to, you can have the best model, or you can have, some insight into how to build a new product around existing AI capabilities. But if you can't run your models in production, if they're not secure, if they're not reliable, if they're not performant enough that you're going to hit your latency targets, if they can't handle throughput, spikes in traffic, top of product hunt, top of Hacker News launch days, then the rest of it kind of doesn't matter. So we really see inference as the centerpiece of this AI infrastructure space around which everything revolves. And we want to, become really, really good at that one central thing, and then over time add on more capabilities.
Mm-hmm. Yeah, I think that makes a lot of sense. I mean, maybe like a rough analogy to that is kind of even like traditional data warehousing, where essentially people like Snowflake came along and separated, compute and storage. So then you have essentially like the query engine. That is like the key thing that you need in analytics in order to be performant. And then you need large storage. And what you're sort of, what you guys are doing and other companies as well are like sort of decomposing this like AI stack. So inference is sort of the compute engine that's important for generative AI. And you're sort of separating that from other parts of it. And then you can focus on like, let's make this thing like really efficient.
Absolutely. And you do need to do more than just get a GPU and put the model on it. With inference, we've been able to learn a lot about, for example, observability and how those metrics and decisions can differ when you're working with an AI part of an AI model within your product, rather than just some ordinary API. So the observability stack looks a little different, the logging looks a little different, and the scaling looks a lot different. Actually, the sort of traffic-based auto scaling that you have to build around that is, something that was surprising to us when we came across the correct answer, because it was, not something you might intuit from previous experience building in other domains.
Mm-hmm. Yeah, I kind of feel like when it comes to a lot of this stuff, you need like a certain amount of like exposure to it, to building up sort of the intuition that comes along with it, to understand like what is the right lever to sort of pull on, or thread to pull on, or thing to do in order to get the performance that you need. Whether that is like from an accuracy standpoint, or even from like a compute standpoint, is you need to build up essentially enough knowledge that some of that stuff becomes innate. And I think one of the challenges right now is that a lot of people, basically this technology hasn't been around long enough for that many people to kind of have their 10,000 hours of building these types of systems.
Absolutely. That's something we've seen even in recent months. For example, you're familiar with the Whisper model for audio transcription?
Yeah.
So it's basically, at the architectural level, a large language model. It has auto-regressive inference. It creates tokens. So with that, familiarity with the model, recently we realized, hey, this is basically an LLM. What if we just treated it as an LLM for model performance? And we used all the same optimizations that we do, like TensorRT LLM for serving Whisper. And turns out it works great. So, like you said, it takes a long time to get sort of familiar and comfortable with this space and be able to start making these connections. But once you do, you get to build and discover really cool things.
Yeah. It's kind of that like building up that general knowledge from like a first principle standpoint, so that then once you've built that expertise, you can start to sort of draw lines to other things that are like, connected to it, or something that maybe from a surface level looks like two different things, but is actually, when you have the expertise, you're able to see like, actually, this problem is kind of the same as this other problem. We can, solve it this way.
I love when that happens, when I run into a new problem and then and then I say, actually, wait, you're an old problem wearing a Scooby-Doo mask. You just take off the mask and hit it with the tried and true solution.
Yeah, exactly. So I want to discuss a bunch of AI related topics with you, and you starting with model selection. Like, I think one of the challenges, especially people kind of jumping into this space right now, is there's just so many models out there. There's closed, there's open source, big, little. When starting some kind of new project, like, how do you even pick? Like, where do you start?
I generally like to recommend that people start with the largest, most capable model when they're in the experimentation phase. Unless there's some constraint that means you can't do that, like if you're building exclusively for edge inference on an iPhone or something. If you're starting with the most capable model, that eliminates one constraint during this experimentation and prototyping process, which is, oh, is my model not good enough? Because you're using the best model. So either the model is capable, or if it's not capable, you need to either go do some custom fine tuning or training work to make it capable, which is a whole other discussion. Or the exact thing you're trying to build isn't quite ready yet. So either wait for the next iteration of the model or figure out a way around those limitations. But anyway, if you start with the biggest, most powerful model, you're able to eliminate that entire category of questioning from your experimentation. You're able to figure out the core flows of your product. You're able to figure out the capabilities that you're looking for, the inputs and outputs that you might expect. And then once you're done with that, then you have all of those other things locked in. Then it starts to make sense to check out different models. Because the thing about model selection is you really need strong evaluation criteria. You can't really just work on vibes and say, hey, this model just feels better. At least you can't at scale. So when you're able to lock those other things in and build a strong set of criteria, and that when I say evals, I don't mean just like building an evals benchmark in the same way as MMLU or any of the other bunch of benchmarks that every new model gets run against. I mean, figuring out for your specific product how you can tell if it's working and how you can tell if it isn't, and then running different models through that. Then you can start trying smaller models to see like, okay, can I save substantial amounts of money on inference by using a smaller model here? You can also try composing multiple models together. Say you've been using a very large sort of everything model, I like to call them, where you have, say, a multimodal model that can do vision and language and maybe audio and speech and everything. Well, maybe you can decompose that, have small, targeted, much cheaper to operate models that handle each of those modalities, and then compose those models all together. You have a lot of options for optimization after that initial prototyping phase. But when you're just playing around, just play around with the best model.
Mm-hmm. Yeah, I mean, I think it's kind of about like you're trying to reduce variance essentially. Like if there's a lot of things that go wrong. Let's take essentially the quality of the model off the table. It's kind of like if you're running an experiment in a company that requires like a person to execute something. it's much better to put probably like your best person on that thing, so that way if it fails, it wasn't the individual that like led to the failure. Whereas if you put somebody who's maybe not so good at that, then it could be, that person was just bad at executing whatever that, project happened to be. In terms of, figuring out whether things are working or not, like what are the strategies there? Like, how do I know whether something is working well or not? And how do I create essentially my own benchmarking mechanism for that, so that when I do go and try a smaller model or a different model, I can test whether I'm reaching the performance that I need or was able to reach before?
So there's, a couple different approaches here. I think the strongest approach is to use a evaluation framework or evaluation library, build a set of test inputs, build a set of expected outputs. There's a sort of LLM as judge pattern that can be very effective here for making sure that you're able to run through large numbers of checks and then have a large language model, perhaps the original model that you were using, judge the quality of those outputs at scale. But it's a tough problem, and there's a reason that there's so many teams and companies working on evals, because it's absolutely critical, but it also can be very dependent on your product. One thing we work a lot with is transcription models, and so we're always looking at word error rate, but you have to drill a little deeper into that. So is it word error rate in general? Is it consistently messing up names? Is it consistently messing up the titles of medicines? There's certain errors that are more impactful than others. So it's a combination of a little bit on the technical side, trying to set up the framework for evaluation, but mostly it's a domain understanding problem where you have to be really clear about what you're trying to accomplish with your system.
Mm-hmm. In terms of like cost savings, if I decide like, oh, okay, I want to like, save some money, I'm going to go and use like an open source model. Then I need to run it. I got to get some GPUs. I got to run my own like cluster and stuff like that. And then I got to manage that thing, handle updates and stuff. Like, am I actually going to save any money that way? like by taking on that work, like, is it really like, I don't know, like an apples to apples comparison there? Like, or is that sort of like a false way to think about potentially saving costs?
That's a great question. It's really total cost of ownership, right? So I think about it less as going from closed models to open models, and more about going from shared inference endpoints to dedicated deployments. Because you can get a shared per token endpoint of Llama 3.1, or on the straw model, you can get for different image generation, Whisper, you can get shared inference endpoints for basically all of the big name open source models. And then just like when you're using the ChatGPT or the OpenAI GPT-4 API, when you're using Anthropic's Claude APIs, you're still paying per token. You're just hitting an endpoint. It's all in the same format. And that is really great in the early stages. If you are, if you're consuming a few thousand, even, a couple 100,000 tokens a day, and you're paying per million tokens, you're probably doing great on those shared inference endpoints. And the additional cost of, having your own GPUs is not going to make sense. But as you scale up, then the economies of scale start to work in your favor. So I generally tell people to switch to a dedicated deployment once they have enough traffic to, consistently saturate a single GPU of whatever type makes sense for their model, because then you're starting to buy your tokens in bulk. But you also get a bunch of other benefits that can make sense, including making sense at somewhat smaller scales. The number one thing, obviously, is privacy. If you are the one running the GPU, then your inputs and outputs can't be, read by OpenAI or anyone else. There's also the customization aspect, where not only are you able to control the model in that you can do fine tuning, LoRa's, you can do an entirely custom model, all that sort of stuff, but you can also control things like setting the batch size to trade off between latency and throughput to get your exact cost characteristics while still hitting your latency SLAs. So there's a bunch of, aspects of control, privacy, reliability, not having, noisy neighbors. Someone hits someone hits the endpoint with 1 million requests and now all your stuff is slow. All that stuff just doesn't happen when you have dedicated deployments. So they can have a better total cost of ownership story once you reach scale, or if you have certain, regulatory or compliance things, or just, privacy concerns.
Mm-hmm. And in terms of like saturating a GPU, what's that look like?
Yeah, so I'm not saying you need 100% utilization of a GPU at all times, but generally, what I'm looking for is a sort of high volume traffic pattern that is, well, it doesn't have to be super consistent and predictable. Scaling GPUs up and down, while difficult, is pretty doable. So you can get pretty fast cold starts denominated in seconds in many cases for these GPUs. It's really more about just having enough traffic so that you're running, batches of inference. Generally, you're running multiple requests at the same time. Because if I have a whole H100 just for, or a whole, in this case, 2 or 4 H100s, just for me to play with the new Nemotron model, then that's a big waste of compute resources. But if I'm, sending through some pretty consistent, stable traffic, then I'm actually, getting the benefits of buying my tokens in bulk.
Mm-hmm. Okay. All right. So we've reached, we got our model. We figured out whether we're gonna rely on a shared inference endpoint or we're gonna essentially run this myself. When does it make sense for somebody to fine tune a model?
So I saw there's this great tweet that goes around a lot. No GPUs before PMF, which is the idea that you shouldn't be making these very capital intensive investments in training and fine tuning ahead of figuring out what you actually want to build. And of course, there are exceptions. If you're a foundation model lab, obviously you need the GPUs to get the PMF. But if you are just, if you're just building a product, I do think that fine tuning is in many cases kind of the last thing you should reach for. It has a ton of useful applications, and there's a bunch of places where it makes sense to use. But first, obviously prompting, and then patterns like retrieval augmented generation, if you want to feed in real-time data. But overall, when I think about fine tuning, it's less about changing the information in the model. That's really what RAG has sorted out. It's more about changing the behavior of the model. So you can fine tune a model to add, say, like function calling. If it doesn't support it out of the box, you can fine tune a model to do better at math or code or something, or some specific domain. We work with a writer who they trained from scratch over fine tuning, but makes these domain specific models for stuff like medicine and finance. That can also be achieved in some cases through fine tuning. But it's really, again, more about changing the behavior of the model versus changing the knowledge of the model, where fine tuning starts to be super useful.
So you mentioned earlier this idea of like sort of stringing multiple models together, like this concept of compound AI. And that's something I've heard a lot of buzz of around this year. Like there was a paper from Berkeley's AI research group, I think earlier this year, that talked about this concept. So I wanted to talk a little bit about that. Like, can you explain, what is compound AI? Like, why are people excited about it?
Yeah, so compound AI, a little bit of a buzzword, but there's a lot of substance there in that you want to basically introduce new capabilities to a model. So we're just talking about fine tuning as one way to do that. But as a, very simple example, let's just talk about math. So, LLMs can't add two numbers together with any degree of reliability. That's just not what they're meant for. So, you can use function calling, you can use tool use to send, a bunch of mathematical functions to the LLM with an explanation of what each one does, along with some parameters. It'll select a function, send it back. You can run that math in, your Python code interpreter, send back the answer, and ask the LLM to provide an explanation. Well, in this super simple, trivial, contrived example, we've made 2 calls to the LLM, and we've done one piece of business logic in between. That's a example of like a multi-step inference. There's also examples of multi-model inference. For example, if you're doing AI phone calling, like Bland is a great example of this. You might have seen the billboards around where it's like, why are you still hiring humans? They have this AI phone calling platform where you call it up and it can do customer support. It can do, ordering a pizza, that kind of stuff. And if you think about it, doing a real-time phone call with AI is three different parts. You need to take what the person on the phone is saying and turn it into words written down, so text. You need to respond to that text using a large language model, and then you need to synthesize that text into speech. So you could accomplish this with a single like Omni type model, but you could generally get much better performance and cost characteristics if you actually compose three models together, one for transcription, one for LLM, and one for speech synthesis. So either of these can be examples of compound AI. Compound AI is a sort of framework of thought. I still haven't come up with exactly the right noun that I want to use for compound AI. It's kind of an architecture pattern for composing multiple models, multiple steps, or both into a single chain of inference with conditional execution logic, business logic, all that stuff baked in.
Yeah, and sometimes, like, correct me if I'm wrong, it's not always necessarily chaining sort of Gen AI models together, but it could actually be like a Gen AI model with traditional ML also plugged in. Like, I think AlphaCode, I believe, does something like that, where they use an LLM to generate like a million potential programming solutions to these like programming problems, and then you use a second. I don't think it's an LLM based model, but they use something else essentially to filter those down to get to the solution that they believe to be the most correct.
Absolutely. I think if you want to look at it at the very highest level, compound AI is about adding specialization back into generative AI. You have these highly capable general models. Like an LLM can do a pretty good job at almost anything. But if you're building these, production ready AI systems that are going to need to be fast, reliable, accurate, then you kind of need to add specialization back in to have an edge. And it's really exciting to work on because now we're building, real applications out of AI, sort of AI native applications, rather than just wrappers around a single capable model.
Yeah. Yeah. It's kind of interesting, this like evolution, because, historically before we had these kind of Gen AI models, like where ML really excelled was something that was like a really specific task. Like you could essentially tune something to do, fraud detection, spam detection, these types of things, classic classification, and it could perform like really well at that. And then the like incredible thing that like blew everybody away with large language models was suddenly you had this like super general thing that you could talk to, and it would answer whatever it would generate some sort of response. But in order to actually, I think, serve a lot of like practical use cases, you need sort of both approaches, because the general model is just going to be like, if it doesn't have a good answer, it might hallucinate something, or like the quality is going to be down, not at the level that you need. So then you need to do something to essentially make it more specialized. And it seems like at the moment where we're seeing the best performance is sort of these like hybrid systems, or this compound AI approach that brings both of these worlds together, of the like specialization and the generalization.
Exactly. You can almost think of the general models as a sort of front end or user interface for these more specialized tools. And, that kind of gets a little bit more into the concept of agents when you start to talk about it like that. But overall, the idea that you have a set of, more granular models, predictive models, or even non-model resources like data storage and code execution, API calls, and that your general language model is just the interface that you're using to interact with all of these things in a new way.
Yeah. So when it comes to, I think like combining models makes a lot of sense, but like, what about the performance? Like already, talking to a model can be relatively slow for a lot of applications, and then now we're talking about like chaining multiple models together, or even, there's models that even in the large models that sort of compete against each other, some of them are better at answering certain types of questions than others. Like probably the best case solution would be you'd put in a prompt and you would fan out to like all the models, and they'd all answer, and then you have another model pick like the best answer or something like that. But that would be a really expensive operationally, and also expensive from probably like a cost perspective. So how do you get the performance out of these systems that can actually serve like these use cases?
Yeah. So, on the quality side, what you're talking about is sort of model routing, and there's a bunch of great teams working on that. I can shout out my friends at Unify are an example of people who are working on that, where if you have like a simple query, maybe it gets sent to a small model. If you have a more complex one, it gets sent to a large model. But the other half of performance is the latency side, right? And the cost, where the difficulty of building with compound AI is that you have to iron out the performance bugs, and the 10 milliseconds of network latency here, and the cold start time there, and the queue backing up at this stage in your graph. That's where having really strong model performance tooling and really strong distributed infrastructure tooling has to come together to make these systems possible.
So in terms of inference, like what is the expensive part of inference? Like why is that particularly like a slow operation?
Yeah, it depends. Let's, for the sake of keeping this podcast under 5 hours, I'll constrain it a little bit, talk just about large language models and other similar autoregressive models. We talked about Whisper before. It has very similar performance characteristics. So there's kind of two phases of LLM inference. There's the prefill phase and there's the token generation phase. So the prefill phase is when the model gets the prompt and needs to come up with the first token. And you're kind of parsing every token within the prompt. This part is GPU compute bound. So in general, the sort of flops or teraflops that your GPU is capable of is going to limit the speed of prefill. And then there's the autoregressive phase, the token generation phase, where the whole previous input plus everything that's been generated gets passed through the model over and over and over again. And this phase is actually going to be bound by GPU memory bandwidth. So, for example, an H100 GPU has 3.35 terabytes per second of GPU memory bandwidth. And that is the limiting factor in many cases on how quickly it can execute a model like Llama 405B, where all of those weights have to be loaded through memory over and over again. So again, if you have, it depends, right? So if you have a case where you're sending a very long prompt and expecting a very short answer, you could potentially be bound on CPU or on GPU compute and have a sort of pre-fill time to the first token problem.
Right.
Or you could, have a more traditional like multi-turn chat, for example, where the LLM is going to be doing a lot of generation, then you have a memory bandwidth problem. I'd say more often than not, we're running into, memory bandwidth versus token versus, prefill, but definitely both make an appearance in just about every performance optimization puzzle.
Mm-hmm. And what are some of the techniques to try to optimize the inference cycle?
Absolutely. So the range of techniques runs from ones that work really well basically all the time to ones that have some pretty meaningful trade-offs. And, it depends. So it depends on your traffic pattern. It also depends on what you're optimizing for. Like you can just say, I want to optimize my model, but that's not really what optimization is. You kind of have to pick a goal and work in that direction at the expense of other things. You could optimize for latency. You could optimize for throughput, for cost. Assuming we're just trying to get like the best possible latencies at a reasonable throughput and cost threshold, which comes from batching. The first thing that basically always works is going to be adding some kind of inference optimization engine. So are you familiar with like VLLM and TensorRT LLM?
Yeah, I mean, at a sort of high level.
Yeah. So, for anyone who's listening who hasn't really heard of these, basically you can take your model weights and you can take like the transformers library for writing inference code in Python, and you can just write some Python code and run it on your GPU, and it'll produce tokens. But there's also inference optimization frameworks like VLLM is a very popular open source one. There's also TensorRT LLM, which is also open source and by NVIDIA. And what these do is provide a set of sort of out-of-the-box optimizations that make the model run faster with almost no downside. With TensorRT LLM in particular, that's what we use very heavily at Baseten. It works by building an engine for your model inference. This engine is a little limited in that it's built for a specific GPU and a specific model. So once you kind of build the engine, you gotta rebuild it if you want to change anything. And the engine can be a little large, which can increase your instance, your image size and your cold start times a bit. But once you actually get it up and running, it's really, really fast because it actually creates optimized CUDA instructions for every part of your model inference process. It's basically almost like compiling your model inference code into these optimized CUDA instructions. And that's something that other inference frameworks don't do. So that's why TensorRT LLM in many cases can have this really excellent performance. So that's kind of step one, is you want to just make sure you're using a serving engine. You want to make sure you're using, of course, appropriate hardware. And then
just one question on TensorRT. So the thing that I've heard, or the criticism I've heard about it, is it's hard to use. So like, what makes it hard to use?
It definitely has a steep learning curve. And again, there's this engine portability problem where you need to create the engine, but then you also need to package it up in a Docker image and go ahead and serve it. I think that the team at NVIDIA is doing a lot to make it easier to use. We've seen things like input and output sequence lengths, which previously had to be kind of set in stone during the engine building process, become more and more flexible, flexibility on batch sizes, that kind of stuff. It's also complicated to use because it provides a very generous API where you're able to twist a lot of knobs yourself and set it up. But yeah, I mean, we definitely have also experienced some of the pains of that developer experience. And that's why at Baseten, we built something called our TensorRT LLM engine builder, where we create a YAML file and specify, the sequence lengths, model weights, GPU count, GPU type, and various optimizations, quantization, that kind of stuff you might want to put in. And then it builds and deploys it automatically for you for, like supported models as well as fine tunes of those models. And that's actually, speaking of our, technically excellent salespeople, we've actually had some of them be deploying models, for demos and customers and stuff using this. So while the TensorRT LLM developer experience can be a little rough under the hood sometimes, for a lot of cases, it's possible to use this tooling to, make it much easier to build these engines.
Mm-hmm. Okay. All right. So base step, basically use an inference engine to help do some of this automatic or like sort of low. I guess the best way to say it is it gives you optimization without a lot of downside. What's next?
So what's next is you start looking at trade-offs between. You've got four sort of levels to play with here. You've got latency, you've got throughput, you've got cost, and you've got quality. So if latency, throughput, and quality are absolutely critical, and the only thing you can be flexible with is cost, throw more GPUs at the problem. I love the solution because, I'm one of the people you can get those GPUs from. But in many cases, you don't want to do that. You want to, keep your cost. That's why you're coming to a dedicated deployment, is so that you can kind of have control over your costs and buy your tokens in bulk, like it's Costco or something. So generally, you start thinking about how to trade off latency and throughput versus quality. And you have to do this very carefully because, when I say trade-off versus quality, hopefully these optimizations that we're doing next have zero impact on the quality of your model output. So it's not so much that you're intentionally losing quality, more that at every step you have to verify your output, run your same evals as you've been running before, and make sure that your model output quality hasn't suffered through this process. Because the first and most important optimization that's out there is quantization. And while we are, constraining our discussion to large language models at the moment, this does actually apply for basically any kind of model. You can quantize, say, like a stable diffusion model and save on inference there as well. So quantization is the idea of changing the number format that your model weights and certain other things like activations, KV cache are expressed in. By default, model weights are almost always expressed in a 16-bit floating point number format. So your model, let's say Llama 405B, has 405 billion parameters. Each one of these parameters is a 16-bit number, 16-bit floating point number, and that's going to be 2 bytes of memory. So all these model weights are, 900 gigabytes of memory, because it's 405 billion times 2 bytes.
Yeah.
So as we discussed earlier, one of the big bottlenecks in inference is going to be your GPU memory bandwidth. So if you could move less weight through that bandwidth, you could move a lot faster. You could do your inference a lot faster. And actually at the beginning, we also talked about prefill and how that's compute bound. Well, your GPU at, a lower precision, it has, every time you cut your precision in half, you double the number of flops that you have access to. So it's a, linear improvement. It's not, you're not from quantization generally going to double your performance. In fact, it'll usually be pretty far from that. But in terms of just like the GPU resources that are available, you would have double the resources if all of your numbers were half as big. So that exists. It's called quantization. It's the idea of converting your data format from, say, a 16-bit float to a 8-bit number format or even a 4-bit number format. Now, the potential downside is a loss of quality because your number format now has a lower dynamic range. So dynamic range is the sort of breadth of values that are able to be expressed. And that's why we've found that the new FP8 format is very impactful here. So rather than going to int8, which is an 8-bit integer number, which has a pretty constrained dynamic range, if you go to FP8, you get a great dynamic range because you're still doing floating point. And this can help with, keeping your model's perplexity gain under control and keeping your output quality very high during quantization and allow you to quantize more than just the weights. And with the new Blackwell GPUs that are coming out, the sort of next generation architecture, we're expecting really great results from FP4, which is a 4-bit floating point quantization format. Currently, if you want to go all the way down to 4 bits, which is popular, especially for local inference, like running models on your, MacBook or something, then you're constrained to those integer formats, which do have that very, very limited dynamic range.
When you lose like quality through quantization, like how does that generally manifest itself?
So the best way to check for that is through something called perplexity gain. So perplexity is a calculation that you can do on a large language model where rather than generating outputs, you actually give it outputs. And then you see how, for lack of a better word, you see how surprised it is by those outputs. You see the number of times where it says, hey, this is not the token that I would have generated here in this known good output. And with your quantized model, you want now there's different ways of calculating perplexity, so it's difficult to do absolute comparisons model to model, for example. But within the same model, if you quantize it, you run your same perplexity check using the same algorithm and same data set again, you generally want your perplexity to not really move at all. There's, a small margin of error, but you don't want to see a gain in perplexity where the model's saying like, hey, before this is the token I would have made and it's a good token, but now this is not, what I would put out. And that's how you see that okay, maybe some of these model weights that you compressed, you got a little, it's not compression, I shouldn't say compressed, but these model weights that you made a little less clear actually were very important and are affecting the output. But again, we've had a ton of success with quantization, especially quantization to FP8, where we're seeing like basically no impact on either the sort of measured quality through things like perplexity or the observed quality through just, consistent customer use and seeing that the model output is satisfactory.
Mm-hmm. What about speculative decoding?
Absolutely. So that's kind of like the next step. So once you have your inference engine in place, once you have your quantization, and by the way, TensorRT LLM can actually quantize your model for you during the engine building process, which is pretty cool. Then you start to look at all of these more exotic approaches to generating more tokens. And this is where it gets really exciting, but it also gets even more dangerous to your output quality. So speculative decoding, there's a few different versions of this. There's one where you can do it with a draft model. There's also a variant that we've used a lot called Medusa, where you kind of fine tune your model to have something called Medusa heads, which are able to create these tokens. But overall, the concept of speculative decoding is if you run, say, Llama 3.23b and you ask it a question, it's going to give you a pretty reasonable response. It's a highly capable model, even though it's super small. But it's not going to be as good a response as Llama, say, like Llama 4 or 5b, which is 150 times bigger. But most of the tokens are going to be the same. At least a lot of the tokens are going to be the same. It, might start, "Hi, my name is." It's going to give a lot of questions, answers that might have, 50% the same tokens. So what if you could get all those tokens from the super small cheat model and only turn to the big model when the small model gets it wrong? So the small model in the speculative decoding setup generates these draft tokens, and then it checks them with the big model. Kind of in the same way that it's a lot easier to tell if a Sudoku is done correctly. You can just scan it really quick and count up all the numbers versus solving it yourself. It's a lot easier to verify that a token is correct. And by easier, I mean like a lot less computationally intensive to verify that a token is correct than it is to generate that token from scratch. So as long as you have a really good verification process, then you're going to get the same output after implementing speculative decoding as you did before. One thing that's interesting with the Medusa approach too is you can actually, during your fine tuning process, where with Medusa, instead of having a draft model, you sort of fine tune your base model so that rather than generating one token at a time, it generates 3 or 4 tokens at a time. One thing that's really interesting with that is you have to fine tune it with some sort of domain awareness because otherwise, like your model might perform just fine at, say, math and then suffer in humanities or something. So all of these approaches, have potential downsides. For example, with speculative decoding, if your draft model gets every single token wrong, well, now you've actually made it slower because you're running the draft model, validating every token and regenerating every token from the larger model. But with, careful implementation, there's definitely a lot of potential for upside with these approaches. You can see, absolutely massive improvements to your tokens per second.
How much do you think like some of these techniques are here to stay versus sort of a moment in time because we haven't developed essentially the chips that can handle the performance that we need?
There are a lot of custom hardware manufacturers who are trying to, take the fight to NVIDIA, which is interesting. And NVIDIA itself, of course, is making new and more powerful graphics cards all the time for this. I do think, though, that within any given hardware or any given model, there's still room for these techniques. So the model and the hardware establish a sort of baseline performance. And then from there, you can layer in all this stuff. So I think I will see, like, as new models come out, as new hardware comes out, these techniques or, all of this is very new applied research. So newer and more efficient techniques are coming out all the time. But you'll see these approaches or approaches like them applied over and over again as these new models and new hardware come out. Because the thing is, it's a lot of work to do this kind of performance optimization and to do it well. You're not going to always see it like day one for every new piece of hardware and every new model. But I do think that over time, these benefits are really going to compound, honestly. If you look at TensorRT LLM, for example, it does, if you run a model on an A100, which is the sort of last generation Ampere big GPU, versus an H100, which is the current generation, you'll see with TensorRT LLM more of an improvement going to the new generation than the baseline hardware specs would imply, because the model's taking advantage, or because TensorRT LLM is taking advantage of the architectural features of these H100 GPUs. And then you get that benefit that's multiplied by the benefit you get from quantizing, that's multiplied by the benefit you get from speculative decoding. So as newer, more efficient models come out, as newer, more powerful GPUs come out, you're going to see even more benefit from using these approaches rather than less.
Right. So, I mean, I think like most people, running a model, building some sort of AI powered application through RAG or something like that, they probably don't necessarily need to be like, looking at the GPU level. But if you are really trying to, squeeze every bit of performance possible out of the inference step, like you probably do need to look at the hardware level. So like you mentioned a couple of different chips. There's a lot of different GPUs, just like there's different CPUs. Like how do those impact the performance on inference? And is there like certain GPUs that make more sense for certain models, or does that matter at all?
Absolutely. It makes a huge impact. And like you said, when you're just starting out, it probably doesn't make sense to look at this GPU level, but it's really a question of like, where do you want your competitive advantage to come from? And if you're committed to a certain model or a certain inference pattern for a long enough period of time to see the benefits, that's where these optimizations can be really useful. In terms of the exact GPUs and their various advantages and disadvantages, so the current generation is Hopper, and that architecture currently is available on the H100 GPU. There's also the H200 GPU, which is even bigger. There's also a GH200, which is a sort of hybrid between the two. And this is really great for running the biggest and latest models, especially because the Hopper and Lovelace, which is the previous architecture, are the ones with support for FP8, which is that really effective quantization format. So within that, though, the smallest memory that's available is 80 gigabytes, which is just complete overkill for a huge class of models, including a lot of image models, which tend to be 12 or fewer billion parameters, as well as, of course, audio transcription models. The largest Whisper model is only a couple billion, if that. So you also have the L4 GPU. That's the previous generation Lovelace, which is, it's a 24 gigabyte GPU. It has much lower memory bandwidth, so it's not great for large language models in many cases, but it's great for some of these image models, some of these audio models, some of these speech synthesis models. You have, the previous generation Ampere cards, which have an A10, you have an A100. Both are great lower cost alternatives to the L4, the H100. Sorry, no, A10s cost more than L4s. But A10s have higher memory bandwidth, so they're good for small language models. You have got like older GPUs like T4s, which are great, for just low cost workloads of small models. And what we see often is people kind of graduating from one GPU to the next. Maybe you've trained a small model that does some specific modality, some new thing, and it runs just fine on T4. Well, eventually, rather than getting your 30th T4 as traffic is picking up, you can start to get better performance and better cost characteristics by consolidating to A10s or L4s. So as it's not just about model. Obviously, model matters a lot because your GPU needs to be big enough to hold your model and your KV cache and your batch inference. But we also see people kind of upgrade over time. And one thing we've done to facilitate that is with H100 GPUs, you can actually split them up through a process called MIG. And no, MIG, unfortunately, is not a cool fighter plane. It stands for multi-instance GPU. With that, you could basically cut an H100 in half, and each half has 40 gigabytes of VRAM. It's got 3/7 of the compute. It's got half of the VRAM bandwidth. And these GPUs offer, these MIG to H100s offer really great performance characteristics for these smaller models. Generally anything under 15, 12 billion parameters can fit on it. They offer you that FP8 access. And then they also have really good price characteristics because you're only paying for half a GPU.
Mm-hmm. Yeah. So, I think we've covered a lot on the performance from, essentially, choosing a model to choosing, essentially an inference engine to, really tuning the inference cycle through quantization and some of these other techniques to picking a GPU. Wait, is there anything else on sort of inference optimization you think that we should touch on?
Yeah, I mean, there's really the whole network layer. There's the whole infrastructure layer that's very important. If you do all of this work to squeeze every second of time to first token out of your model by optimizing prefill, and then you take your GPU and you stick it in, US East 1 in Virginia, and your user is in Australia, then all that model performance work is right out of the window because of the network latency. So there's really two completely separate domains that have to be considered together in highly optimal model serving infrastructure, because it's both this model performance layer and it's also the infrastructure performance layer. So obviously there's locating your GPUs reasonably near to your user. That's important. With compound AI, it's minimizing the network overhead in the multiple hops that you're making from model to model. So yeah, it's definitely that networking and infrastructure component where you have to consider, for example, cold starts. If you're getting a burst of traffic, you need time to scale up those GPUs and load in these very large images and these very large sets of model weights. So being good at that part of it is absolutely essential for doing this in production, because otherwise your really flashy performance metrics are not going to be what your user actually experiences.
Yeah, absolutely. That's a really good call out. At the end of the day, unless you're running this, essentially in a closed system on an edge device, most likely you're making some sort of network call. And then, if that's 900 milliseconds, it doesn't really matter what the performance is like on the actual inference piece.
Exactly. We've even seen stuff as simple as switching from the requests library in Python to doing a connection pooling with HTTP, saving, that extra 10 or 20 milliseconds and making the difference between hitting the latency SLA and not hitting it. So, there's a whole lot of work to be done at the infrastructure and the networking level to actually deliver this excellent performance to the end user.
Also, how much does the programming language choice a factor as well? A lot of people's go-to when you're talking about AI and machine learning is Python, but Python's notoriously not the most performant language in the world. Is that something people need to also be considering?
In some cases, that's where the Inference Engine can help a lot. For example, TensorRT LLM is a C++ model server, basically. Okay, so there's TensorRT LLM. There's also Triton, which is the Triton Inference server. Those two generally go together. And we actually built our own variation of the Triton Inference server that's even more lightweight, but that's also built in C++. So yeah, there's a lot of C++ under the hood in these kind of stacks, and that's going to help a lot with the performance. And of course, the GPU inference part, that's going to be a problem for CUDA to handle. And that's where, again, TensorRT LLM helps out. So yeah, it's, as speaking as someone who is really only comfortable programming in Python and JavaScript, I'm able to, leverage a lot of these tools that people much smarter than I have put together and stand on the shoulders of giants and be able to, write my little Python code and not really worry about performance too much.
Mm-hmm. Awesome. All right. Well, let's switch gears a little bit and go quick fire. So if you could master one skill that you don't have right now, what would it be?
So I would really love to be better at math, which I realized I had a great opportunity to do in college and totally squandered getting a lot of B's in math classes. But I was working on this transformer inference blog post a year ago with someone at Baseten, and he's an engineer there, and he was sort of explaining to me the actual math behind figuring out, like, how do we prove that this inference is bound by GPU memory bandwidth rather than something else. And just looking at these papers and all of the Q, K, and V and stuff, I like it when math has numbers in it, not letters. So it would be really cool if I could be a lot better at some of this math behind the inference. But I'm learning it slowly but surely.
Yeah, never too late. What wastes the most time in the day?
Definitely uncertainty. Working at a startup, there's always a lot of stuff going on. It's like, oh, what should I work on? What should I do? Is this right? Is this good enough? Should I, spend time on this or that? Uncertainty and just not pulling the trigger and making a decision is where I probably waste the most time.
Mm-hmm. If you could invest in one company that's not the company you work for, who would it be?
There's this great company called Pylon. They do customer support. We're customers of them. I'm friends with the founders. They were actually in Chicago the other day, and I tried to tell them, like, hey, I'll trade you, like, a couple hundred of my shares for a couple hundred of your shares, and they didn't go for it. But they're a great company. They're working super hard. They have a lot of customers, including us, who really love them, and they're taking on some incumbents like Zendesk that I think are ripe for disruption. So yeah, big fan of Pylon.
Cool. What tool or technology could you not live without?
Honestly, it sounds super simple. It's Markdown support in Google Docs. I was so happy when that first came out because I use Google Docs for basically everything I do just because everyone has it and it's super easy to work with. And just not having to train the Markdown shortcuts out of my fingers to use it has been really nice.
Mm-hmm. Which person influenced you the most in your career?
I wanna shout out a couple people. There's this guy Lee Robinson who's also from Iowa. I was raised in Des Moines, Iowa. So I often say that I want Baseten to become Vosel and I want Philip to become Lee. So that's a pretty simple way of me expressing my career goals. But I've also been influenced a lot by Patrick McKenzie, who goes by Patio 11 on a lot of internet spaces. I've really appreciated his writing on startups and entrepreneurship, and found a lot of wisdom there. So, yeah, those are some of the very, very long list of influences.
Yeah, good picks. So, and then finally, 5 years from now, will there be more people writing code or less?
Never bet against coders.
Yeah, I mean, I always feel like that an engineer's job is to solve problems. That's why you get paid the money that you get paid. So at the end of the day, like, that's not necessarily about sort of hands on keyboard. It's about, like, essentially solving problems. So maybe the manifestation or the evolution of that is you're doing a lot more prompting to generate code that you're sort of working with, but you're still, essentially solving problems and putting these things together.
Absolutely. I mean, there's some days with my job that spans all these different departments and functions. There's definitely days where I don't write code, but I still feel like I'm a software engineer, even when I'm solving these other problems, just because it's more about the mindset and the approach you have to solve the problem rather than the exact problem you're solving.
Yeah, I don't think the engineering mindset doesn't go away. So, all right. Well, Philip, thanks so much for being here. I enjoyed this a lot. Cheers.
Yeah, thank you so much for having me. This was a really fun time.